Okay, so continuing on with our example, the last two portions of this example, we're going to look at adding in or testing whether or not the slope for the London reading test varies across groups. So, in other words, is there a significant variation in the slopes across groups, and should we then incorporate that into the model? And then if the slope is randomly varying across groups, then the next question is, can we add in level 2 predictors of that variation? So the first step is basically going to be involved testing the random slope to see if it is statistically significant, or if the variance is statistically significantly different from zero. So you'll notice that now we're adding to our model. In our previous examples, our level 1 equation is this. Our level 2 equation that incorporated a level 2 predictor, which was essentially the school mean on the London reading test, was being used as a predictor of variation in the intercepts across schools. Those intercepts reflecting an adjusted mean on exam performance. Uh, we also incorporated the level 1 predictor, and we had the fixed effect right there, and we were treating that effect as being fixed across the groups. Now we're going to add in a random component right here, which is the deviation of a given group's slope from the grand mean of the slopes across the groups. So we're allowing then the intercept to randomly vary across the groups. So through substitution, things get a little bit more convoluted, but you can see right here, this, and this, these are all portions of the level 2 equation that were substituted at level 1. And then you've got essentially the fixed effect. We're substituting this information right here for beta subscript 1j. And so we've got essentially that component. And then we also have the random component that's also being multiplied by the x variable at level 1. And then we have the level 1 residual. So to model this, we are now going to go into our data set and click on linear, continue. We're going to click on random. And so now we're going to allow this, we're going to move this variable over to this box. And this is going to indicate then that the slopes, the regression slopes for the London reading test at level 1 should vary across level 2 units. So the slopes become essentially a level 2 outcome variable in the model. Okay, so and at this point we're only going to be modeling variation in the slopes, and then later on, if this is statistically significant, then we will unpack that and see if we can't model predictors of that variation. So at this point, because we now are modeling the slope coefficients, a variation in the slope coefficients, we now are going to have a variance at level 2 for this. So in a nutshell, we have variation in the intercepts, which is the variance of mu 0j, and we also are going to have the variance of the slope coefficients, which is the mu, and we're going to call it 1j, and then potentially, so the variance component, if we leave variance components clicked, we are simply going to be estimating the variances of those two parameters. The next component, though, is that we could theoretically model the covariance between the intercepts and the slopes across groups. So in other words, we could theoretically model the covariance between those two components if we want. And so if we want to do that, we can just click on this button right here, go to unstructured. And so what it will do is it will calculate or model the variance of the intercepts, variance of the slopes, and then also the covariance between them across the groups. I'll be honest, a lot of times what happens is that, well, I won't say a lot of times, but it does happen that by doing this, you're estimating an additional parameter, and so what can happen is that the data becomes too complex for the model to be correctly estimated. And so, so then you get sort of a nasty little warning message. It looks like it's worse than it is, but basically what you have to do is you have to then maybe simplify the model. And so you might then choose to go back to the variance component or something like that. But for this illustration, we're going to stick with unstructured and click on continue. We're going to leave our estimation method as it was before, statistics as before, and we'll click on OK. And so now you can see that at this point we've added in for the random effects, this is the mu oj, this is the mu 1j, and so so there you go. And we've also, because we've asked for a covariance structure that's unstructured, we now are estimating 3 parameters. So we're estimating the variance of the intercepts, the variance of the slopes, and then also the covariance between those two. And that's why you have 3 parameters being estimated here instead of 2. These are the level 1 residuals, that the variance of the level 1 residuals, and then these are our 3 fixed effects in the model. Scrolling down, you can see here that we've got, we have our intercept, so this is the gamma 0, 0 that we've had before. This is the gamma 1, 0 that we've had before for the fixed effect of London reading test on exam performance at level 1, and then we also have the gamma 01, which is modeling school average for London reading tests as a predictor of variation in the intercepts, which is basically indirectly modeling the relationship between the context variable and the level 1 outcome, since the level 1 outcome is in part a function of the school mean. All right, so now we look at the estimates of covariance parameters. So we have the level 1 residual. We see that it is still statistically significant, meaning that there's still variation to be had at level 1. And then now you'll notice you've got the little UN, and so the 1, 1. So you just have to kind of think about this as that covariance matrix I was showing you before. So the 1, 1 is basically the variance for the intercepts. The 2, 2 is the variance of the slopes. So there's the 1j right there. So I mean, if you think about this, it's sort of a little matrix right here. This is the primary diagonal, so this is essentially, row 1, column 1, and then row 2, column 2 right here, and then you've got essentially row 2, column 1. So there's row 2, column 1, and that's the covariance between those two. So I'll just I'll just give it a little sigma there, little eraser. And so that's the covariance of I'll just say a little cove down here, covariance for the intercept and the slope. So there you go. So that's why it looks like this. So in terms of these estimates right here, the variance of the intercepts is still statistically significant. The variance of the slopes is still statistically significant. And then there's actually significant covariation between the intercepts and slopes in the model. So there you go. Now, given that we have significant variation in the slopes, we might want to predict that variation. And so things can get a little bit more complicated in the model. In this case, we're basically modeling a cross-level interaction between the school average London reading test scores and the level 1 predictor for London reading test scores. So we'll go to Analyze, Mixed Models, Linear, Continue, and so again, we have the slopes already randomly varying across groups. So now we're going to go to Fixed, and in this case, now we're going to create an interaction term. So we're going to click on Build Nested Terms, and it doesn't matter the order, but so I'm going to put this variable in down here by this variable here, and then click Add, and so that creates an interaction term. So you don't actually have to create an interaction term using compute functions in SPSS. You can just do this, and this will accomplish that. So click on Continue, and then on OK. And so now you can see that we have the fixed effect for the interaction between the level 1 predictor and level 2 predictor. We still have our three variance components at level 2, which is the variance of the intercept, variance of the slope, and the covariance between them. We have the variance of the residuals at level 1, and then we also have the additional three fixed effects that we had in the model previously. So now when I scroll down, you'll notice that we've got, again, there's our intercept. This is our fixed effect for the level 1 predictor. It's still statistically significant. The fixed effect for the level 2 predictor also is statistically significant. But then we also see that we have a significant interaction between the level 1 and level 2 variables. So in other words, I might take this to mean that essentially the school average London reading test scores is a moderator of the relationship between the level 1 London reading test variable and student exam performance. So another way of putting this is that we have cross-level interaction that is taking place. So given that significant interaction, the next logical question is, well, can we plot the interaction, kind of get a visual idea about what's going on? Essentially what this means is that the relationship between the level 1 predictor and the dependent measure exam score, that the slope coefficient is increasing by this amount for every 1 unit increase on the level 2 predictor. So, but I oftentimes like to get a visual on this, and so this is a visual of the simple slopes, where basically we have this broken out into schools that have lower average London reading test scores, medium London reading test scores, and high levels of or high average London reading test scores. And so you can see that. So then essentially the x-axis is levels of the London reading test scores at the individual level or level 1, and then the y-axis is the exam performance or exam score at level 1. So you can see then that essentially the relationship between London reading test scores and exam performance is actually more pronounced or most pronounced in the high group or the high in those schools that have higher average scores on London reading test scores, and it's less pronounced in those schools where you have medium or medium average London reading test scores and low average London reading test scores. So yeah. So how did I generate the plot? Basically, I just have a little calculator in Excel, and I use that. So this is my little calculator right here that I've worked up. And so it's essentially just kind of feeding information into this little calculator. So just kind of illustrate what I'm talking about. What I need are the descriptive statistics for the level 1 predictor, which is student London reading test scores. So I'm just going to generate descriptives here and then add in standardized London reading test scores. That's my predictor variable. Under options, I've got my mean standard deviation. So I've got here, can't really see it very well in this example, but there they are. There's the mean standard deviation. And so what I'll do is I will just kind of go in here and I'll just type that in. So I'm just going to call this LRL, or London Reading Test at level 1. And click on the mean. And in this case, I will, the mean is 0.00, I'll just round off to 0.002. And standard deviation is 0.993. Okay, and then for the level 2, it's a little trickier. If both of my variables, if I was modeling an interaction at level 1, then I could just generate descriptors for both of those and feed those in. But because the level 2 is based on the number of schools, then I need to take into account the variation in the intercepts for level 2, or variation in the school means on London Reading Test at level 2, because that's our predictor. So I'm going to call this LRT level 2, or I'll just call this LRT mean L2. And essentially then I've got to generate those school means. So unfortunately in this data set right here, the school level and the student level data are all incorporated into the same file. A lot of times life is a lot easier if you actually have separate files for the, or at least two individual files with that would also contain the school level predictors. So I really need to be able to compute the mean and standard deviation. If I do it using the just descriptives, it will be based on all of the student level data as opposed to the school level mean data. So to get around that problem, the strategy that I'm kind of suggesting is maybe kind of trick your way through SPSS and basically fool the program into generating the school mean. So what I'm going to do is I'm going to go through the univariate option and run a one-way ANOVA. Now, before you get too sidetracked, all I'm doing is trying to get some information. So I don't care about any ANOVA results themselves. All I'm trying to do is get the school means isolated from the data set that's aggregating for all the students. So I'm just going to move my grouping variable over here, click on the standardized LRT mean, and under options I'm going to move school ID over here, and I'm leaving really everything blank because I don't care about anything along the lines of the ANOVA. In fact, you can see nothing is going to come out of that because of what I've done. But I don't care. I'm more interested in obtaining, here we have the school means, and essentially if I just kind of click on copy special, and I'm going to copy for an Excel worksheet, and essentially I'm going to open up a new Excel worksheet and paste that in, and so now I can compute the mean and standard deviation for that variable across the schools. So you've got schools, you have all 65 of those schools, and so that's how it's going to be done. So I'm just going to type in average all the way down. There's the average of the school means, and then the average of the standard deviation for the school means. Okay, so the average of the school means is negative 0.031. So I'm going to go in here, I'm going to type in negative 0.031. Standard deviation is going to be the 0.344 roughly. So I'm going to type in 0.344. All right, so now I need to type in the regression parameters from the model. So you can see right up here that we've got, let me find it here. So the intercept is negative 0.007. Negative 0.007. The X is essentially my level 1 predictor, London Reading Test. So it is going to be 0.558. Okay, and then we're going to add in the moderator, the slope for the moderator, or the level 2 moderator is 0.373. And then also take into account the interaction term. The slope for the interaction term is 0.162. All right, and there you go. That's how we got the graph.